So today we're going to talk about hypothesis tests for population means. Let us start reading what's going on here, getting ready for the contents, the formulas. In earlier lessons, we learned that there are two basic forms of statistical inferences. The very first one is the confidence interval that we delved into. We learned how to form the confidence interval for population proportion and also population means. And the other one that we're going to focus on is hypothesis test. In earlier lessons, we constructed confidence interval for a population mean. Now we will test the hypothesis that a population mean is equal to a specific value or not. So our goal is hypothesis testing for this lesson. We use the four-step hypothesis testing process. So let us go over one example to feel more comfortable about hypothesis testing. Some people believe that the Earth's magnetic field guides some animals as they travel over great distances. However, it is not clear how these animals detect the Earth's magnetic field. The monarch butterfly is an example of an animal that may travel this way. These butterflies can survive a long cold winter. So they migrate long distances south in the fall. These butterflies fly to the same winter roosts year after year. Often they fly to the same trees each winter. It's not known how they locate their winter homes. One possibility is that they have some magnetic material in their bodies that allows them to sense a magnetic field. Okay. Biologists wanted to determine whether these butterflies have some magnetic material in their bodies or not. So these scientists used a tool called magnetometer for this test. The magnetometer measures electromagnetic units that are called nanometers. Unfortunately, the magnetometer itself creates some magnetic intensity. Well, so it compromised the measurement. The magnetometer creates about 20 units of magnetic intensity. Well, each unit is 10 to power -9. Guys, this number is very small. Remember that when you have a negative exponent, 10 to -9 is the same as 1 divided by 10 to +9. Well, if we calculate this number using our calculator, this is going to be very, very small. It's near 0. Okay, in order to demonstrate that butterflies have some magnetic materials in their bodies, the scientists needed to be able to show that these butterflies mean magnetic intensity is greater than 20 units. So we're dealing with the mean. As a statistician, you're looking for keywords. In this case, the keyword is the mean. For this test, we will use a 5% level of significance. So 5% level of significance. Do not confuse 5% level of significance with level of confidence. When it comes to confidence interval, we are dealing with confidence level. So now that we are dealing with hypothesis testing, we are working with level of significance. We will assume that the population of magnetic intensities in these butterflies is actually normally distributed. Very well. Let us go over the steps how to identify the hypothesis test that we have. Before doing that, let me write something here for you. Very well. When it comes to hypothesis testing, we are either dealing with hypothesis test for population, mean, or population proportion. So remember, population mean denoted by mu, and population proportion was denoted by P. Let us focus on population mean. So when we have hypothesis testing for population mean, we have three different scenarios. The first scenario, the second scenario, and the third one. In the first scenario, what you have is two hypotheses. The very first one is called the null hypothesis, denoted by H sub 0. Its opposite is alternative hypothesis, denoted by H sub A. So we have null hypothesis and we have alternative hypothesis. Well, null hypothesis says the mean of the population is larger than or equal to a number like K. Its opposite is the mean is less than K. When you read a question, either the null hypothesis is given to you or the alternative hypothesis is given to you, one of them. For example, if the alternative hypothesis is given to us in the question, we can quickly construct the null hypothesis, which says mean is larger than or equal to. So this is our very first scenario, our very first case. If you read a question and you constructed the null hypothesis, alternative hypothesis, and it is the first scenario, then we construct the left-tailed graph, because our alternative hypothesis says mean is less than. So in this case, we have a left-tailed graph. How does it work for a left-tailed graph? You're going to shade a very small portion of the normal graph on its left-hand side. mu is less than k, so we're going to have a left-tailed graph. Left-tailed. We shade the left tail of the graph. This is our case 1. This is our first scenario. The null hypothesis says the mean is larger than or equal to k. Alternative hypothesis, which is the opposite of null hypothesis, says mean is less than k. So this is less than, smaller than. This is larger than or equal to. And you get left-tailed graph. We're going to use these graphs later on to reject or fail to reject the null hypothesis. The second case is, well, your null hypothesis says, hey, mean is less than or equal to a number like k. Its opposite, alternative hypothesis, is mean is larger than k. The opposite of less than or equal to is larger than, greater than. So in this case, since the alternative hypothesis is larger than, greater than, it means that you're dealing with a graph and we shade right-hand side of the graph, right-tailed. This is going to be your right-tailed graph. We shade right-hand side of the graph. Later on, we're going to learn how to find these numbers dividing the rejection region from non-rejection region. So this is called right-tailed graph. And finally, in the last scenario, the null hypothesis says the mean of the population is the same as number like k, and its alternative says mean is not equal to k. It is not the same as k. As you can see, these two are opposite of each other. Not the same. Not equal. So when it's not equal, it means that it's either on the left or on the right. So we're going to have a two-tailed graph. Two-tailed graph. It means that we shade a little bit on the left, a little bit on the right of our graph, and we have a two-tailed graph. Two-tailed graph. So as you can see, as you noticed, what do we have here? In our null hypothesis, we have equality present somewhere, greater than or equal to. When you're constructing your null hypothesis, you must have equality. Null hypothesis, mean is less than or equal to k. Null hypothesis, mean is k. It is equal to k. So this portion that is not shaded is called non-rejection region. So this part, the shaded part, is rejection region. The same here, the part that is not shaded is called non-rejection region, and this little part that is shaded is your rejection region. And for the two-tailed graph, the middle area is non-rejection rejection region. Later on, we're going to see if our test statistic is inside the non-rejection region or outside the non-rejection region, which is rejection region. How do we deal with our null hypothesis? Let us get back to our example here. So step one, we're interested in our hypothesis. Which one is our null hypothesis? Which one is our alternative hypothesis? The null hypothesis says the population mean is equal to specific value. So null hypothesis, mu is equal to k. So the alternative hypothesis is one of the following. Null hypothesis is equal to k, greater than equal to k, less than equal to k. It has equality somewhere. And your alternative hypothesis, it doesn't have any equality. It's either less than, larger than, or simply not equal to. So for this example, state the null and alternative hypothesis. Is it left-tailed, right-tailed, or is it two-tailed? So let us get back to our example here. This is the experiment that we have here. We're looking for keywords. So remember that when you're constructing your null hypothesis, alternative hypothesis, you're looking for keyword like larger than or equal to, less than or equal to, larger than, equal to, not equal to. Our job as a statistician is to look for keywords. Okay. After reading each of these lines carefully, remember that we want to know and collect information about the mean. On the last line, we say that, hey, the biologists needed to be able to show that these butterflies' mean magnetic intensity is greater than. The keyword is given to us, greater than. So what is given to us? Greater than, which scenario is this? Is it the first scenario? Is this the second scenario? Is this the third scenario? It says greater than, the keyword is greater than, larger than. So what's given to us? Our alternative hypothesis is given to us in this example. So we can easily form the null hypothesis, which is less than or equal to. It means that we are dealing with right-tailed graph. So again, the keyword is greater than. It means that it is the second scenario. In the second scenario, our alternative hypothesis is given. Mean is larger than k. K is the number. What is that number? 20. So this is your k. Okay. So here, our alternative hypothesis is given to us because the keyword greater than is given in the example. It means that our alternative hypothesis says mean is greater than, larger than k. What is k? K is 20. This guy is given in this question. Your null hypothesis is not given, but it's very simple to construct the null hypothesis because null hypothesis is the opposite of alternative hypothesis. Mean is less than or equals to 20. Since our alternative hypothesis is given larger than, it means that we have a right-tailed graph. Right-tailed graph. It means that we shade the right-hand side of the graph. This is our rejection region, and this is our non-rejection region. So the answer is, it is a right-tailed graph. Well, let's take a look at question 2. Question 2 says, the biologist examined a random sample of 16 monarch butterflies. So N is 16. From the population, they took a sample of 16 of them. The measured magnetic intensity of each butterfly is given in the table below. Okay, remember that. We don't have all the information about the population. So we're taking random samples and we're not worried about normality because in previous page, it was mentioned that this is a normal distribution. So the sample size 16, we're fine with that. They took a random sample of 16 butterflies. They measured the magnetic intensity of these butterflies, and these are the information that we have. Are the criteria for approximate normality of sampling distribution of sample means satisfied? Yes, of course. Yes, because since the population is normal. That's the reason. We're happy about the normality. We don't have any problem here. So now you have a collection of data. You have 16 numbers. What should we do with these numbers? Remember that as a statistician, the very first thing that you need to find is the mean. Then you need to find the standard deviation. So you need to ask this question. What is X bar? What is the sample mean? This is our sample mean. And what is the standard deviation of our sample? We're going to use our calculator to calculate these numbers. Let's move this a little bit here. Calculator. So let's turn on the calculator, clear this. Let's go to Stat, Edit. So we're going to clear all of these, delete them one by one. Entered a lot of information here. Okay, perfect. You can also just reset the whole thing to make sure that you don't have any built-in functions, built-in formulas. So you can go to second class, reset your calculator. Second class, reset the defaults. And go to stat, edit, and enter all of these numbers that you have. 48.6, enter, 32.8, 53.2, 32.3, 17.3, 12.2, 36.6, 29.8, 12.4, 21.9, 26.4, 49, 14.5, 7.5, 40.2, 29. Okay, so let's go to stat. Let's go to calc, one variable stats. Every information is in L1. So let us calculate. As you can see, X bar, or the mean of the sample, is 28.98. 28.98. And standard deviation of the sample, we're not working with sigma, we're working with S. Sigma is for the population. We don't have information about population. We only have information about sample. So S of X, 14.15. Okay, what's next? So in our next step, we're interested in finding the test, standardized test. So since we are dealing with S, we cannot find Z. What are we going to find? We're going to find T. Very well, okay. Remember the formula for your T, test statistic. T is equal to X bar minus mu divided by S over square root of N. So let us calculate our T. Our T is equal to, what is our X bar? 28.98 minus the mean. Well, what is our mean? Our mean from previous page is 20 divided by S. S, we calculated S. S is 14.15 divided by square root of N. N is 16. So square root of 16. If you use our calculator, we get 2.54 as our T. This is your test statistic. So why do we need this? If this T is inside the rejection region, you're going to reject the null hypothesis. If T is outside the rejection region, if it's inside the non-rejection region, we fail to reject the null hypothesis. Remember that null hypothesis says mean is less than or equals to 20 units. Alternative hypothesis says mean is larger than 20 units. This is our educated guess. We collected data. We found X bar, we found S. Now we need our test statistic related to the sample. And then this is 2.54. If T is inside the rejection region, you're going to reject the null hypothesis. So if T is in the red shade, we reject the null hypothesis. This is what we're trying to decide about. If T, this number that we calculated based on this sample, is inside this rejection area, rejection shade, we're going to reject the null hypothesis. We're going to say that, hey, mean is not less than or equals to 20. It probably is larger than 20. But how do we determine if T is inside this area or not? The thing that you need is this number here, this critical number that divides the rejection region and non-rejection region. How do we calculate this number? This is our goal. We want to know what is that critical value that helps us to decide about this T. How do we know this T is inside the rejection area or not? So remember that in previous page, the information that we had was about 5% level of significance. And I told you this 5% level of significance is different from the level of confidence that we learned in when we formed the confidence interval. Now we're going to move on to learn how to find this critical value that divides the rejection region from non-rejection region. Very well. So we're going to use our calculator to help us decide about this test. Okay. Take a look at your calculator, the instruction that you need to use. I'm going to write that down here. The instruction how to use your calculator. So when you are using your paper to decide which one of these scenarios to use, and then you have your calculator instruction down here. So first of all, you go to Stat, you enter all of the information that you need there. So go to Stat, go to Edit, enter the numbers. Okay, then you go to Stat. Now you need to go to Tests. This is hypothesis testing, so we're going to go to Test. Remember that we calculated the T, not Z, because we don't have information about population standard deviation. So you're going to select T-test, then you're going to use the data that you entered there. So you're going to select the data and move to the next line. And so here you have data. Mu sub 0 is your K. Mu sub 0 is your K. In this case, our K is 20. Well, X bar is the mean of our sample, which we calculated before. X bar is the mean of the sample. S sub X is the standard deviation of your sample. Then n is 16. Well, we know that. In this example, we know that alternative hypothesis says, hey, the mean is larger than k, and k is the same as mu sub 0. So we're going to select the last case, larger than k. K is mu sub 0. You can go to calculate now. So after entering all of this information, go to calculate. We're looking for the p-value. What is our p-value? P-value is the area of this rejection regions. P-value. So p-value is given to us as, if you take a look at this, this is very small. It's almost 1%. So p is almost 1%. This is what are you looking for. When you're following these steps, you need to find the p-value, which in this example is 1%. Each example has a different p-value. So what are you looking for is your p-value. So in our example, our p-value is this guy here is almost 1%. 1%. Okay, so 0.01%. This is our p-value. Now, your p-value is less than 5% that is given in the question. You're right. Since p-value, which is 1%, is less than the 5% level of significance, so we reject the null hypothesis. This is our conclusion. Since p-value is less than 5% the level of significance, we reject the null hypothesis. At 5% level of significance, there is enough evidence to conclude that the mean is larger than 20. Again, at 5% level of significance, there is enough evidence to conclude that the mean is larger than 20. Because p-value is 1%, it is less than 5%, so we reject the null hypothesis. This hypothesis is not supported. It means that its alternative, its opposite, is supported. At 5% level of significance, there are enough evidence to conclude that the mean is larger than 20. Let us check another example. Okay. Mean lifespan of batteries. Imagine that a company sells portable walkie-talkie radios to construction crews. The batteries for these radios last for an average. Okay, I'm a statistician. I'm going to pause a little bit, think about this, an average of 55 hours. So this is important. The average lifespan is 55 hours. So it's important information for me. The purchasing manager for this company receives a brochure in the mail that advertises a new brand of batteries. This new brand of batteries is cheaper than the brand that the company currently uses. But the purchasing manager is concerned that the cheaper batteries may have a shorter average battery life than the current brand, which is 55 hours. Okay, note, the number of hours that batteries last is called their battery life. The pricing manager wants to perform a statistical test. So the manager hires you as the statistician to help him or her to run this test. The level of significance, last time it was 5%, now it's getting smaller and it is just 1%. So another important information is 1% level of significance. So your job as a statistician is follow the steps. What is the scenario that you're dealing with? Is it the first scenario? Is it the second scenario? Is it the third scenario? And the rest of them. Okay. To determine whether the cheaper batteries have a shorter, smaller average battery life. Okay, the keyword, I found my keyword. Do they have a shorter or smaller average battery life? It means that my alternative hypothesis is given. Shorter, smaller, less than. This is the first scenario. And in this question, alternative hypothesis is given to me. So alternative hypothesis says the mean is shorter than 55 hours. Shorter, alternative, even though the null hypothesis is not given to me, but I can quickly form the null hypothesis. It's just the opposite of alternative hypothesis. Mean is larger than or equals to 55 hours. Is it left-tailed, right-tailed, two-tailed? As I know, this is my first scenario. It means that I have my rejection region on the left-hand side, so I'm dealing with left-tailed graph. Left-tailed, okay. This is a left-tailed graph. It means that the rejection region is on the left-hand side. And this area here, is my p-value. Remember that your job is to find your p-value. If the p-value is less than 1%, then you reject the null hypothesis. Otherwise, you say you fail to reject the null hypothesis. Okay, now let us move on to next step. To test this hypothesis, the pricing manager installs 40 randomly selected batteries. Well, what is 40? 40 is my N, the sample size of the new brand in the company's walkie-talkie radios. He finds that the mean lifespan for this sample is 52 hours. What is this guy? This is 52 hours, the mean lifespan of the sample. So X bar is 52. And the standard deviation is also given to me as 10 hours. I have all the information that I need. S is 10. Now, as a statistician, your job is to decide to reject or fail to reject the null hypothesis. I'm not really worried about the normality because my sample size is large enough. It's 40. I can quickly go to my calculator and calculate the p-value. Now we need the p-value. Okay, here we go. Let us bring our calculator here and then enter the information that we need. So first of all, this example is different from the example that we did before. We don't have the actual numbers. So we're not going to enter any number in our calculator in StatEdit. No L1, no L2, nothing like that. So what are we going to do then? We're going to go to Stat. We're going to directly go to Tests. So we don't have this sample data. This is the thing that you need to note. So you go to Stat and you directly go to Tests. Now, since you have information about the sample, you need to go to t-test. T-test. See? Yes. Okay, t-test. I don't have the data. What I have statistics about the sample. What are those statistics? Those are X bar and S. So you're going to select stats. Not the data. In previous example, we had the data, so we used the data. In this example, we don't have the data. We're going to use stats. So what is my K? What is my K? What is my mu sub 0? Mu sub 0 or K is given as 55. So it is 55. What is X bar? X bar is 52. Let's enter all of these. Then what is standard deviation? Standard deviation is 10. It's given to me. Somebody already calculated those. And what is N? N is 40. How about my alternative hypothesis? My alternative hypothesis says, hey, mean is less than K. Less than K. So we're going to select less than K. Okay, very well. Let us go to calculate. Well, it calculated p-value for me. The p-value, or this little area here, is almost 3%. 3%. P-value, or P, is almost 3%. Is 3% less than 1%? P-value is not less than 1% or the level of significance. What's the meaning of that? It means that we fail to reject the null hypothesis, or in a sense, we support the null hypothesis. P-value is not less than the level of significance, so we fail to reject the null hypothesis, or in a sense, we support the null hypothesis. What's the meaning of that? It means that at 1% level of significance, we have enough evidence to support the null hypothesis. So at 1% level of significance, there is not enough evidence to conclude that the mean battery life is shorter than 55%. You're rejecting with 1% level of significance, and the evidence that we have, you're rejecting the alternative hypothesis. You're supporting the hypothesis that the mean is greater than or equals to 55.